first thing we're going to talk about is a relation. And when you hear the term relation, a relation is just a set of ordered pairs. So keep in mind, in any ordered pair, you have an XY format or an XY combination. Based on the rectangular coordinate system, you can find the exact location of any point in your rectangular coordinate system with the use of an ordered pair. Now, as far as an ordered pair is concerned, the X values, they represent your domain values. The Y values, they simply represent your range, right? So we have an XY ordered pair format. A relation would simply be a set of ordered pairs. So here's an example. Okay, we have a relation (3, 1). So normally in a relation, it's a set of ordered pairs. So we have 3, 1 is our first ordered pair. Our second ordered pair is -2, 9. Next we have 4, 3. And then last we have 3, -1. All right, so this is a relation, right? It's just a set of ordered pairs. So I guess in order to group these things, okay, I'm going to use a set of curly braces. All right, so we want to find the domain and the range. Okay, so our domain values are simply all of our X coordinates. So we have 3 as a domain value, -2 as a domain value, 4 as a domain value. Okay, we have -3 as a domain value again, so we don't actually list it twice. Right, so these are our domain values. Now we'll take a look at the range values. So the range would simply be the Y values. So we have 1, 9, 3, and -1. Right, so in the simplest form, a relation is just a set of ordered pairs. The X coordinate is your domain, the Y coordinate is your range. Okay, we'll come back to this example a little bit later, and we will determine if it is in fact a function or not. So next we're going to talk about a function. Pull this up a little bit. All right, and by definition, a function is a relation in which each element in the domain, so these are your X coordinates, corresponds to exactly one element in the range. Right, so the range would be your Y coordinate. Then it says if X represents any element in the domain, then X is called the independent variable. If Y represents any element in the range, then Y is your dependent variable. And now independent and dependent, these are just what they represent. Okay, but as far as the domain in the range and determining if it's a function, it doesn't matter if you're dealing with an independent or a dependent variable. All right, so now we're going to take a look at a function. And we're going to determine if a graph is a function. We're going to look at this function concept under a few umbrellas. First, you'll have to determine if a relation is a function. Then you'll have to determine if a graph is a function. You also have to be able to determine if an equation itself is a function. And so we're going to be looking at it and as relations, graphs, and equations. All right, so now here we have a graph, and we're asked from this graph to give the domain and the range. So now as far as a graph is concerned, the domain is all of the x values that your graph takes on. Another way to look at the domain is it's the stretch of your graph across, in this case, the x-axis. So if I take a look at our graph, the domain, it runs from -3 to +3. Right? So that would be the domain for this function. It would be -3 to +3. And I can't actually write that. Let's see. Well, I can actually write on here. I'll write it on the document camera. All right, next we're looking for the range. All right, so notice this vertical stretch on the y-axis. These are all of the y values that our graph takes on. These are our range values. Whenever you write out your interval notation solution, you must make sure that in interval notation, the leftmost coordinate is the smallest number. So for example, the range for this particular oval would be from -6 to +6. All right, so I'm going to go to the document camera to actually write that out. So we would write the domain as -3 to +3. I'm using a set of brackets because the graph actually touches -3 and it actually touches +3. Okay, therefore, I'm using a set of brackets. For our range, looking again at the graph, the range is from -6, including -6, right, because it actually touches -6 on the y-axis, to +6. Okay, and I'm going to use a set of brackets. All right, so we just looked at a graph, and from the graph we're able to determine the domain and the range. Just remember that the domain is the stretch across the x-axis. The range is the stretch across the y-axis. All right. Now in the definition of a function that we had just taken a look at, right, there was another part, right? It says that as far as a relation is concerned, okay, we just dealt with a graph. But as far as a relation is concerned, each element in the domain has to correspond to exactly one element in the range. So now let's determine if a relation is a function. All right, so we're going to go back to this previous example. All right, we were given this relation. We were asked to find the domain. We were asked to find the range. Is the relation a function? Okay. So how do we determine if this relation is a function? In order to do so, we're going to proceed with what's called a mapping. Right, so we're going to use what's called a mapping. So this is how a mapping works. We're going to list all the domain. We're going to list out our domains in one column. We're going to list out our range in another column. And then we're simply going to map the domain to the range. And we want to keep the definition of a function in mind. Does each element in the domain correspond to exactly one element in the range? All right. So let's map out this relation. So in this first column, I'm going to list out all of our domain values, which we would determine were 3, -2, and 4. Our range, we have the values 1, 9, 3, and -1. Right, so now we're going to perform our mapping. So if we look back at our ordered pairs, 3 maps to 1. So I'm simply going to map 3 to 1 with a line. -2 maps to 9. Right, so I'm going to map -2 to 9. 4 maps to 3. And 3 maps to -1. Right, now we're going to take a look at the definition. The definition says, I'm going to kind of abbreviate it over here. And this is for a function. Each element in the domain, which is X, corresponds or maps to exactly one element in the range. All right. So automatically it seems that 4, it maps to exactly one thing. Doesn't really matter what it maps to, just as long as there's only one line coming from each domain, right? So 4 maps to 3, which is exactly one thing. -2 maps to 9, so -2 corresponds to exactly one element in the range. But keep in mind that for 3 corresponds to more than one element in the range. So based on the fact that 3 corresponds to more than exactly one element in the range, this is not a function. All right, simply because we have 3, which maps to 2, right, items, which makes it not a function. All right, let's take a look at another example. All right, so same directions, find the domain and range. So here we have 4, 6. We have 2, 6. We have 5, 1. All right, so I'm going to give you a second. I want you to list out the domain. I want you to list out the range and determine, is it a function? So is the relation a function? All right, so I'll give you a couple of minutes or so to write everything out. All right, so let's take a look. So for our domain, we have 4, 2, and 5. Our range values are 6 and 1. Right, no need to list 6 twice. In order to determine if this relation is a function, we're going to map out the domain and the range. So our domain values are 4, 2, and 5. Our range values are 6 and 1. Right, so 4 maps to 6. 2 maps to 6. And 5 maps to 1. So is this a relation? And the answer would be yes. This relation is a function. So if we check with the definition, 4 maps to exactly one element, 2 maps to exactly one element, right? Doesn't really matter if they map to the same thing, but what we're looking for is there should only be one line stemming from every domain value. Okay, it doesn't matter about the range, right? We simply don't want any repeating x values. So since we do not have any repeating x values, this relation is a function. All right, so we're able to take a relation. We were able to pull out the domain. We were able to pull out the range. We were able to determine if it is a function. Okay, so now we're going to take a look at a graph, right, which is this graph that we looked at earlier. And how can you determine if a graph is a function? Okay, we can pull out the domain and the range, right? We can pull out the stretch across the x-axis as our domain values. We can pull out the stretch across the y-axis as our range values. But in order to determine if a graph is a function, you must perform what's called a vertical line test. And a vertical line test says that if you draw a vertical line such that you have no more than one point of intersection, then the graph is the graph of a function. So let's take a look at a couple of examples. All right, here we have two graphs. All right, we have a parabola, a U-shaped graph, and we also have a circle. All right, and we have to determine if these graphs are the graphs of functions. So let's take a look at the red graph first. In order to determine if it's a function, you would simply draw a vertical line. Right, so this dashed line is the vertical line that was chosen to be drawn. If there's no more than one point of intersection, so notice that this vertical line, it touches or intersects our graph at no more than one point. So this graph is the graph of a function because it passes the vertical line test. Now let's take a look at the green graph, which is the graph of a circle. So if we were to apply the vertical line test to a circle, notice that we have more than one point of intersection, right? We actually have 2 points of intersection. So the green graph is not a function, right? So in order to determine the domain and the range, right? The domain follows X, the range follows Y. To determine if that graph is a function, you must perform a vertical line test. Now, as an exercise to you, all right, here is a graph. Okay, I'm going to give you a minute, and I would like for you to give the domain. I would like for you to give the range, and I would also like for you to determine if this graph is the graph of a function. All right, so I'll give you a minute or so to do that, and then we'll take a look at the solution. All right, so let's take a look at the solution. And let's see if I actually have it here. All right, so let's take a look. So here we asked to give the domain and the range for each one of these graphs. All right, so our domain. Now, this graph, even though it appears to actually stop, right, this graph actually keeps extending forever upward. Right, so this graph actually keeps on spreading out, right, making that U shape. So what's the domain? Now, if you look kind of close on this, you're going to see these arrowheads, which means that this graph, it would, in time, stretch the entire x-axis. Right, so notice there's an arrowhead here, there's an arrowhead here, which means that this graph stretches the entire span of the x-axis. So how do you write out its domain? Well, we're going to simply write out the domain as all real numbers in interval notation. So we're going to write it out as a parenthesis negative infinity, comma, positive infinity. So what do these infinity symbols mean? Well, these are like a sideways 8, and it means that positive infinity means the values for x get larger and larger and larger and never stop. Negative infinity alludes to the number gets smaller and smaller and smaller and smaller and never stops. Negative infinity. Whenever you denote positive or negative infinity, you must always encapsulate with a parenthesis, never with a bracket. Okay, a bracket implies that it stops. Infinity never stops. Negative infinity never stops. So our domain is all real numbers. So now what's our range? So as we look at the vertical line for our range, notice that it actually stops or starts here, right? And then the graph continues to stretch the entire positive y-axis. So what's our range? Well, it looks like this graph spans on the y-axis from -3. And since it looks as if the line touches -3, I'm going to use, and this is subjective. Some people may see it hit, some people may not see it hit, but this is just an example. All right, so this actually hits the -3y value, so I'm going to encapsulate -3 with a bracket, comma, positive infinity with a parenthesis. Right, so this is our range. It's the half open interval from -3 to infinity. All right, so now we will take a look at a function. All right, so what we've done so far is we have described the relation. We're able to determine the domain, range, and if the relation is a function. We did the same thing with a graph. If you're given a graph, you can find the domain, you can find the range, you can determine if that graph is a function. Okay. But what if you're given something, an equation? For example, function or not. So let's say we have 4x is equal to 3y plus 2. Let's say we have x squared plus y squared equals to 9. And then let's say we have y is equal to x squared plus 1. All right, so we're not given relations, we're not given graphs, we're given equations, and we have to determine if the equation is a function or not. All right, so in essence, what you would do is you would graph the functions, use a vertical line test, determine if that graph is a function. Now, later on in the course, we're going to talk about something called the algebra of functions. And in the algebra of functions, we look at the linear, quadratic, cubic, so on and so forth. we give a general model form and also a general idea of the sketch of its graph. Okay. But for now, if we just look at 4x plus 3y equal to 2, and if you wanted to determine if this was a function or not, you would basically solve it for y, graph it, and determine from the graph if the graph is a function. So here's what I mean. So here we have 4x plus 3y equal to 2. So I'm going to solve it for y and graph, right? So if I were to solve this for y, I would subtract 2 from both sides. And I'm kind of rearranging this around some. And I would divide both sides by 3. Right, so I basically just rearrange the equation. So if you were to graph this equation, y is equal to 4/3 x minus 2/3, would this graph give you the graph of a function? And the answer would be yes. Right, keep in mind that this is actually slope-intercept form, y is equal to mx plus b, where this is your y-intercept, negative 2/3. 4/3 is your slope, right? So since this is a positive slope, if we were to graph this, the line would look in general something like this, right? Because of that positive slope. So this would be a function, right? So that first example is a function. Okay, the second one, x squared plus y squared equals to 9. Well, it's x squared y squared equals to 9. This is actually the equation for a circle with a radius of 3. And I know that from kind of dealing with functions, but nonetheless, you could solve it for y and you could graph. So just to show that in a little bit of detail, I'm going to solve this for y and graph it. All right, so I'm going to solve it for y. So the first thing I'm going to do is subtract x squared from both sides. Right, I want to solve for y, not for y squared. So I'm going to take the square roots of both sides. And remember from intermediate algebra, the square root property says that if x squared equal to c, the variables may have been different in your previous scores, but if x squared equals to c, then x equal to plus or minus the square root of c. And this was that square root property. So that means that if I'm solving this for y, I'm going to take the plus or minus square root. So y is equal to plus or minus the square root of x squared plus 9. This plus or minus actually breaks this thing into two. Excuse me, this should be negative x squared plus 9. This plus or minus breaks this into two equations. So I have y is equal to the square root of negative x squared plus 9. And I also have y is equal to negative square root of negative x squared plus 9. I'm going to graph this on calculator. All right, so I'm going to graph this on the calculator. All right, so I'm going to go into y equals, and I'm going to clear out any equations. I'm going to put in the square root of negative, right? So I'm using the negative, not the minus. Negative x squared plus 9, right? Close off your square root. For y sub 2, I want to put in a negative square root of negative x squared plus 9. I'm going to use zoom 6 to graph. And notice that this is the graph of a circle. It looks oval shaped, but if you were to zoom standard, it would, I'm sorry, not zoom standard. It is zoom square, I believe. It would just make it appear to be more circular. All right, but that is in fact the equation of a circle. So if you were to apply a horizontal line, a vertical line test, it would fail. Right, so that equation x squared plus y squared plus 9 is not a function. All right, so when you graph, you have a circle with a radius of 3. Right, you apply a vertical line test, and it is not a function. All right, and what about our last y is equal to x squared plus 1? All right, well, this would be the graph of a parabola. Okay, it's already solved for y. So if you were to put that into the calculator, x squared plus 1, so I'm back at y equals. I'm going to clear out those functions. I'm going to put in x squared plus 1. I'm going to use zoom 6 to graph. All right, so we have a parabola or a U-shaped graph, which is what a quadratic equation produces. So will it pass a vertical line test? And the answer is yes. So y equal to x squared plus 1 is a function. All right, so x squared plus 1 is a function. All right, so now we will get into this domain range concept a little further. All right, so we have an ordered pair which is in an x comma y format. Right? In this x, y format, our x coordinate is the domain. Our y coordinate is the range. Also, x, which is the domain, that's also an input. Y, which is the range, that's also an output.